Hello and welcome. This is the 25th Annual Wilderness Issues Lecture Series, Connecting Landscapes, Conservation Across Boundaries. I'm Lori Young. I'm the Interim Director of the Wilderness Institute here at the College of Forestry and Conservation at the University of Montana. So last week, Raphael Chacon, art historian here at the University of Montana, talked about changing cultural perceptions of wilderness and nature with a focus on landscape painters and how they characterize the American West in the context of white settlement and manifest destiny. This week we're going to shift gears and we're going to look at the biological context of landscape conservation, in particular watersheds and hydrological connectivity. And so we're just really excited to have Catherine Pringle from the University of Georgia join us to talk about what she calls a neglected dimension of conservation biology, hydrological connectivity. This lecture is co-sponsored by the Bitterroot Ecosystem Management Research Project. It's also made possible by the work of an undergraduate, Clint Cook. Can you raise your hand, Clint? Thank you, Clint. Clint has worked with the Bitterroot Ecosystem Management Research Project for his internship and his senior project and helped to bring Catherine from the University of Georgia to talk with us about hydrological connectivity. So to introduce Catherine this evening, we have Alan Watson, a social scientist with the Aldo Leopold Wilderness Research Institute, which is an interagency research organization housed just on the south end of campus here. Alan is also on the executive committee for the Bitterroot Ecosystem Management Research Project, and he'll be telling you a little bit more about Catherine. Thank you.
So I'll introduce Catherine, and Catherine's going to introduce Lori, and Lori's going to introduce... It's a pleasure for representing the Leopold Institute and the Bitterroot Ecosystem Management Research Project. How many of you know what that is? Yeah, not very many. It's a local group. The university, Rocky Mountain Research Station, the Forest Service, Northern Region of the Forest Service, and the Bitterroot National Forest are kind of a unit that's trying to work on applied research. And we're working on some watershed issues down the Bitterroot National Forest, primarily trying to understand the relationship between the Selway Bitterroot Wilderness, some of the streams coming out of that wilderness, some of the dams in those streams, some of those human alterations to those streams, and kind of the ecological integrity of the place and the quality of life in the Bitterroot Valley. So what Clint did was help us in making contact with Catherine, inviting her, and we're just really pleased to work with the University Wilderness Institute to sponsor her visit here. She did a lecture today at the Rocky Mountain Research Station. Tomorrow she's going to be down at the Bitterroot National Forest giving a very similar type of discussion, presentation with those managers. So Catherine is a professor of ecology at the Institute of Ecology at the University of Georgia. All of her degrees, undergraduate and graduate degrees, are from the University of Michigan in Ann Arbor. Her current research, and the part that we really focused on and why we invited her here, was on the ecological consequences of hydrologic alterations and other human disturbances in freshwater ecosystems. And you're going to see slides and hear her talk about such neat places that she's worked as Costa Rica, Puerto Rico. The University of Montana has a strong relationship with some programs in South Africa. We happen to hear today that she's done some work at Kruger National Park, so we asked her to tell us about that a little bit. And so we'll see where that goes. But she's particularly interested in linking research to resource management, and beyond that, to outreach, environmental outreach, conservation, education outreach. So she's worked with National Science Foundation, Environmental Protection Agency, the Forest Service, even Nature Conservancy and National Geographic Society. Right now she's the chair of the Ecological Society of America's Sustainable Biosphere Initiative. So with that, let's welcome Catherine.
Thank you. It's a real pleasure to be here today, addressing you at the 25th Annual Wilderness Lecture Series. Thanks very much for the introduction. What I hope to do today is give you a broad stroke picture of what hydrologic connectivity is. It's been a neglected dimension of conservation biology. I can't do a lot in an hour. I'm going to paint a broad stroke picture. What I really want to do is generate a lot of questions within you regarding the water quality and quantity issues here in the Missoula area and also in the Bitterroot Valley and other adjacent areas. The plan I'm going to follow here for the talk is to talk about what hydrologic connectivity is and why it's been ignored within the field of conservation biology. Is that better? You guys couldn't hear me in the back before? Sorry. Okay. You didn't miss much. Okay. Is that better? I really should talk into the microphone and not at my slides. Okay. So I'm going to talk about hydrologic connectivity, a neglected dimension of conservation biology, and I'm going to follow this outline. I want to define what hydrologic connectivity is and why it's been ignored by the field of conservation biology, then talk about the scope and magnitude of alterations in hydrologic connections globally. And then I'm going to move into why we need to manage hydrologic connections to protect wilderness areas and protected areas in general. And then talk about some of the interacting effects of altered connectivity in contaminant transport, and then leave you with some questions, some future challenges. Okay. I'm using hydrologic connectivity here in an ecological context. This property has been essential in maintaining the ecological integrity of landscapes. I define it as water-mediated transfer of matter, energy, and organisms within or between elements of the hydrologic cycle. Things like dams, water withdrawals, these things can disrupt hydrologic connections in rivers and in groundwater. Additionally, hydrologic connectivity perpetuates the flow of elements in the landscape, and it can be a double-edged sword in that it perpetuates the flow of harmful things like contaminants and nutrients that it can eutrophy systems. Now, riverine connectivity has long been acknowledged by the scientific community. Jack Stanford, who's right here in your backyard, is the director of the Flathead Lake Biological Station, has written some seminal papers with James Ward defining riverine connectivity in this way. He talks about the longitudinal, lateral, and vertical dimensions of connectivity. Longitudinal from the headwaters to the estuaries. Vertical, the groundwater stream channel dimension. Lateral, the interaction of the stream channel with the floodplain and with the riparian zone. A stream is not just the channel. It's this interaction of all these different spatial components. Now, consideration of the dynamics along these three different spatial dimensions has proven to be a very effective conceptual framework to view the human impacts on river ecosystems. Dams and flow regulation not only fragment the river channel longitudinally, but oftentimes you put a dam in and you regulate the flow beneath the dam, you're disrupting the connectivity between the stream channel and its lateral linkages with the riparian zone and floodplains. And this is essential for the health of the ecosystem. So I can't say enough about what James Ward and other colleagues have contributed to this whole aspect of connectivity. Henri de Camps, Robin Welcome, and others have also been instrumental. Now, here we have this knowledge out there, but it's just not been considered by the conservation community. It's really important that we disseminate this body of knowledge and it gets incorporated into conservation biology. It's appalling when you realize that rivers are often not even considered in the scientific literature. Can you hear me in the back? In the scientific literature that deals with management and conservation of fragmented landscapes. In these major books on habitat fragmentation written by leading conservation biologists, they don't even mention stream or river. Many of you will be familiar with the critical-sized ecosystem project in Manaus, Brazil, where the World Wildlife Foundation and various other organizations are monitoring biodiversity through time on different sized forest fragments. They have 100-hectare plots of rainforest surrounded by pasture, 10-hectare plots, and so on. They never even used the presence or absence of surface water, rivers or streams, as a criterion in picking their sites. You've got all this debate in the literature about whether several large or several small reserves are better, the SLOSS debate, but very rarely do conservation biologists ever talk about the position of a protected area in the hydroscape within the watershed. Some of the reasons for this: one main reason is we never really acknowledged until the last decade or so that groundwaters and surface waters were integrally connected. I highly recommend a U.S. Geological Survey manual that was put out by Winter et al. And it's just a wonderful primer, if you will, environmental literacy on groundwater and how it's integrally connected with surface water. Also, hydrologic connectivity is often ignored until water quality and quantity problems become crisis issues. And that's because of a lack of data we have in general of hydrology in the landscape. Okay, so I'm going to move on here to the scope and magnitude of hydrologic alterations on a global scale. It's kind of depressing. You've probably heard a lot of it before. I want to get through this part quickly. And I want to move on to why we have to very actively manage hydrologic connectivity to protect biological reserves. Because these reserves are embedded in a matrix of hydrologic disconnectivity that we have imposed on the landscape. The first trend I want to talk about is large rivers and the fragmentations of large rivers along their main stems. Rivers are really not, in many cases, flowing water systems per se anymore. They're a series of lakes connected by highly regulated flow regimes. A lot of our children see a reservoir and they think that that is a lake, when in fact it is an impounded piece of stream, of once moving stream. There's all kinds of consequences to this, not just decrease in economically important fishes like salmonids, which we hear about a lot, particularly in the Pacific Northwest here, but there's all kinds of other animals that are affected. You've got decreases in a lot of uneconomically important fish species. They used to be predominant in eastern rivers: shad, striped bass. You've got all these riverine species that are no longer dominant in these systems because they're so highly altered. You've got exotic species that are oftentimes stocked into these artificial lakes, and a lot of lake-adapted species take over, and so on. So there's a lot of consequences to this. The next trend I want to mention here is the deterioration of river deltas, estuaries, and receiving coastal waters. These rivers empty into the ocean. There's a lot of consequences when you dam them and have many, many dams upstream. Many of the world's major rivers are facing large environmental problems related to hydrological modifications. You've probably heard a lot of this before. The Colorado River you know about, just a trickle when it reaches the Gulf. The St. Lawrence River, the Yellow River in China, the Ganges River in India, even the Volga, which empties into the Caspian Sea, has been reduced in volume by 74% before it enters the sea. As a result, you have reduced salinities, increased salinities of the receiving waters. Many of the rivers aren't flowing all year anymore, and so that freshwater input is gone. You get deltas in coastal areas that are often sediment starved because the sediments that would normally be deposited on the coast, on the delta, are deposited behind dams upstream. That's the case here in the eroding Louisiana Delta, where you have a dike that's trying to prevent erosion and loss of shoreline. This is happening worldwide. The Black Sea, where the Danube enters into it, the Danube's so heavily dammed upstream. There's incredible coastal erosion on the Black Sea at the mouth, and so on. You've got a lot of those coastal areas very dramatically affected, mangrove declines, and so on. Okay, the third trend I want to mention is riverine floodplain, wetland, and riparian ecosystem decline. We've oftentimes mismanaged our floodplains by building right up to the edge, as you can see here. And the statistics are alarming. The US and Europe have lost half of their wetlands, Asia 27%, and so on. You can look at these statistics. It's happening all over the world. you lose that integral connection of the river channel and its floodplain. The fourth trend I want to mention is irrigated lands and connecting surface waters and some of the environmental problems associated with this, which I'll talk about later in the lecture also. 10% of the world's irrigated land suffers from salt buildup. Water tables are falling on every continent. In an area of north-central China inhabited by 100 million people, the water table has fallen 30 to 35 meters over the last 2 to 3 decades. The last trend I'm going to mention is often unacknowledged by people, and that is the deterioration of upstream headwater areas that are often protected in parks and reserves. These areas have their habitat intact, but there's so much disturbance downstream that you have that disturbance transmitted upstream and causing changes in the ecosystem. In a paper I wrote in 1997, I talked about going against the flow, how disturbance is transmitted upstream. And I discuss how downstream disturbances like urbanization and dams, can you hear me back there? These disturbances can be transmitted upstream. You've got isolated populations of fishes up there perhaps that can no longer breed with other populations from other tributary networks. If you lose some of those populations and they go extinct because they can't migrate down to the ocean, for instance, you might get entire aspects of the ecosystem changing. Maybe those animals were important to ecosystem processes like primary production or like decomposition. Think, for instance, of salmonids. You lose them when they come back to lay their eggs and their bodies die, and they die and decompose. They're bringing essential nutrients to the system. Those nutrients are no longer present. Algal primary production changes. So there's a whole trophic cascade that can occur here. Okay. So I just went through some of these emerging patterns that are occurring globally. And all of these things are happening such that to such a great extent and magnitude that a lot of our protected areas are just embedded in this matrix of disconnectivity. So we really do have to actively manage hydrologic connectivity as a property when we're managing our parks and protected areas. And that brings me to the third part of my outline, managing hydrologic connectivity to protect biological reserves. Less than 7% of the world's land area is either strictly or partially protected. Many reserves are in danger of becoming population sinks for wildlife. That is, wildlife may go there, but they may not reproduce successfully. It's really essential that we don't let this happen and that we develop a more predictive understanding of hydrologic connections and how disrupting these connections can affect the biological integrity of protected areas. A lot of these hydrologic alterations happen outside of the boundaries of protected areas. This is one of my favorite pictures I found in a book of poetry on gardening. Here's the Garden of Eden. Oops, sorry. And a river is coming into this walled garden. Let's think of a protected area here, and two rivers come out of it. Well, clearly this area is very vulnerable to hydrologic alterations outside of its boundaries. Water extraction upstream and so on. So as I said, the location of a biological reserve within the hydroscape has been a neglected dimension in terms of conservation biology. Hundreds of thousands of dollars have been spent researching whether one large reserve is better than several small. As I mentioned, this is called the SLOSS debate, several large or several small, SLOSS. And it's been a real contentious point in conservation biology. And yet people just ignore whether a reserve is in the lower watershed or if it's in the upper watershed. They've ignored the position of regional aquifers and wind and precipitation patterns, which are equally important. In a paper that I wrote for ecological applications in 2001. I just made this schematic diagram showing the consequences of disturbance to reserves that were located in the lower, middle, and upper watershed. And basically what you have here is here's a reserve in the lower watershed, and you've got water extraction here, you've got sewage input here. The reserve is getting directly affected downstream of the perturbation. In the middle watershed, you can have perturbations above and below the reserve. And in an upper watershed location, you can have this disturbance that's transmitted upstream. And I just want to give you a few examples from protected areas that you might be familiar with and others that are outside of the country. I'm having trouble operating all of these gadgets. Okay. Before I do that, I'll just mention the trend here. A lot of times the middle and lower watershed reserves that are located in that location oftentimes suffer direct habitat alteration and modification. There's altered flow regimes because of dams upstream, a lot of pollution, that kind of thing, and you can get a lot of cascading trophic effects. The same thing can occur in the upper watershed, but the habitat is often left intact. But you start to lose conspicuous elements of the biota, of fishes and shrimps and various other animals. And you oftentimes get genetic isolation of source populations. And this has not been acknowledged until recently. This doesn't just affect the aquatic ecosystem. Think of the cascading atrophic effects on higher trophic levels. When salmonids don't migrate upstream, what do the bald eagles eat? What do the bears eat? And so on. I'll give you two examples here of headwater parks. Parks located in stream headwater areas. One from the Pacific Northwest, the Olympic National Park. You're probably all familiar with this story. Okay, that's that. There used to be 10 stocks of salmon that used to run up these rivers, and the Elwha Dam and the Glines Canyon Dam here caused these runs to be extirpated, if you will. So you don't get these essential nutrients coming up the system. You have trophic cascades. The reservoirs associated with these dams also flood large areas of the valley, and so when elk want to go down and during seasonal migrations to lowland areas to overwinter, they cannot pass easily. You've got a different situation in the tropics, in the Caribbean National Forest in Puerto Rico, where you have headwater streams that are dammed below, and there's lots of water intakes outside of the forest and also some within. In this situation, you've got a migratory fauna, but it's very different than the salmonids. It's these freshwater shrimps that I'm going to talk about a little bit later. So it's really clear that these streams and upper watersheds are not impervious to disturbances downstream. This is just two examples of many. I wanted to throw in the Kruger Park, located in South Africa. Kruger Park's much larger than the two different reserves I just showed you, the National Forest and the National Park in the previous slide. It's the size of Israel, and I believe it's about 100,000 kilometers squared. The entire park has a fence around it. It's located in South Africa on the border between Mozambique and South Africa, and I've got it changed its position here. This is really north here, and this is south. But I just wanted to show you how inappropriately positioned this park was in terms of vulnerability to hydrologic disconnectivity. Here you have the major rivers bisecting the park right through the park lies right in the middle, basically. You've got hundreds of thousands of people living in some of these river basins, like the Olifants River, for example. There's 30 dams on this river. And so what happens is, in this beautiful park, we have all the big game species. It's a very arid environment, getting very low rainfall. You've got rivers that were once perennial like this, with stable hippo populations and other animals that depend on the water, becoming intermittent streams with sandy bottoms like this during much of the year. All the animals that live directly in the water, directly dependent on it for habitat, are very affected. What the Park Service tried to do to alleviate this problem was drill wells in between these rivers so that the animals could exploit this territory and not have to be dependent on streams that were intermittent. And what happened is very interesting. Here's an example of one of the wells that they drilled. It's this little water hole. Windmills drive the power and bring the water up. What happened was all the grazing ungulates within the ecosystem, giraffes and all the other animals that graze the forage, the terrestrial vegetation, they took advantage of the water supplies being increased, but they overgrazed their food source. And so you had these peaks and crashes in population of the grazers. Giraffes would reach super high levels, overgraze, and then die of starvation. And the predator populations, things like hyenas, lions, and so on, would then peak in response, and then they would crash. So it became very clear that this management strategy to deal with hydrologic disconnectivity was not going to work, and they're now phasing out these boreholes. And they're back to trying to promote minimum in-stream flows in those rivers to try and minimize water extraction upstream, which is very hard in an impoverished nation like South Africa. But they're actually making great progress, and it's a success story. This is one of the largest parks when you consider park size worldwide. And that's all I had to say about Kruger. I just couldn't resist putting that in, knowing there was a South Africa connection here. Okay, so we just talked about some reserves located in different watershed locations. But that's not the whole story here. We also have to consider reserve location beyond the watershed. We have to consider regional aquifers, where a reserve is located with respect to groundwater supplies, and also where it's located with respect to wind and precipitation patterns. And then also, how is global climate change going to have a broader feedback loop and affect our parks and reserves? So this is just a schematic to talk about, to illustrate how reserves can be affected by hydrologic alterations and pollution outside their boundaries, outside the watershed, excuse me. Here you have the watershed demarcation, the red line. Everything's draining into this river. Here's a factory outside of the watershed, and the wind is blowing in that direction, and so you get lots of acid rain and nitrate deposition on this park. So the problem isn't even within the watershed. You can have the same kind of thing with a regional aquifer. Here's an aquifer or groundwater that goes beyond the boundaries of the watershed, and drilling and well water extraction for irrigation outside of the reserve is affecting the integrity of the reserve outside of the watershed. Excuse me. We've got, as a result, parks throughout the world that are being affected by nitrate deposition and acid rain. Parks from Acadia Park in the eastern U.S., Great Smoky Mountain National Park, to Kruger Park in South Africa, Tatra Mountains Park in Poland. This is an example, this is a really nice illustration, I think, of how the Great Smoky Mountain Park is really in a difficult situation. These are acid rain levels, pH. The pH of rain, 4.2 in this zone, 4.5 in this zone, and here is where the Smoky Mountains National Park lies. Because of nitrate deposition, you've got a lot of forest die-off, and in fact, this federal public land, this national park, has some of the highest recorded nitrate depositions of all parks in the U.S. Okay, talking about aquifers now, I just wanted to give you two examples that were kind of interesting to me. I had no idea that the geyser activity at Yellowstone was at one point threatened by drilling and drilling for natural gas outside of the park's boundary. Here you have Yellowstone Park, and there's a lot of geothermal features, as you know. drilling for natural gas here affected the hydrostatic pressure and was going to actually affect the geyser. It was affected one geyser right here. And so apparently of the 10 major geysers that are really dramatic geysers in the world, all but 3 of them have been altered already by similar kinds of perturbations. In any case, because this is a jewel in the crown of our national park system, Yellowstone has been protected, and now people that are doing drilling and water extraction outside of the park's boundaries have to prove beyond a shadow of a doubt that they will not affect the groundwater or the hydrostatic pressure so that the geysers will be affected. Death Valley National Park, it's actually a park now, is also affected by hydrologic alterations of groundwater outside of its boundaries and the watershed per se. These water intakes indicate where wells are being drilled in the Las Vegas area to feed a very thirsty population. These little blue tadpole-like symbols are the location of springs within the Death Valley National Park, and it's feared that the dropping groundwater table is going to affect these springs here in the park. Not to mention, you've got the nuclear waste dump, Yucca Mountain, I believe it's pronounced. I'm not sure. Just up there. And hydrologists are still arguing over how fast that stuff could move towards that particular park. Okay, so if you look at our national forests and our public lands as a function of increasing population growth, as this figure indicates, with the progressively darker colors indicating higher population numbers, and these are projected percent increases of population per 1,000 people from 1995 to 2025, with the highest percent increase expected in the western states here. You can see how vulnerable these areas are going to be to increased water demand from outside their boundaries. This is the national forest. Here's the national parks. I've circled some of the parks I'm going to talk about. Yellowstone I mentioned already, Olympic Park up there, and the Death Valley National Park to the bottom left. Now, as a result of this increasing pressure on water resources provided by these federal lands, the federal managers and personnel are having to deal increasingly with the proliferation of proposals for water development near national parks and forests. The National Park Service is presently participating in water rights adjudications in 7 states involving 38 western parks. This data is 5 years old. In order to get it, I called up representatives from federal agencies and asked them this because this information is not readily available. Federal agencies don't advertise when they're in litigation or in adjudications for water rights. The U.S. Forest Service currently has 500 legal claims pending for water rights in national forests located in 11 western states and 55 basins. Now look at wildlife refuges. They're even more vulnerable because of their small size, high edge ratio to surface area. And in talking to Cheryl Willis with the Fish and Wildlife Service, she told me some pretty startling anecdotal information. Of the 226 western refuges responding to a 1994 questionnaire, only 98 reported that their existing water rights were adequate in an average year. Many people don't realize that a lot of our wildlife refuges actually buy water back from irrigation projects to support their wildlife needs. And this came as I was astonished at this. So how can we, given this information, more effectively manage hydrologic connectivity on landscape scales outside of parks and reserves? We really have to do this. We have to take advantage of every single tool we can to do it. We've got to do all of these things. We've got to establish in-stream flow requirements. make sure that enough water is flowing over the dam to support the biological integrity of the system. We can change dam operating criteria when dams come up for relicensing through the Federal Energy Regulatory Commission. We can remove dams. We can choose to put dams in. Kruger Park is actually dependent on some dams to release water from the reservoirs during particularly dry periods now. The Park Service manages those dams. I'm going to talk about some other negative aspects of removing dams a little bit later. But then you can go on here, you can talk about dam maintenance, you can talk about water diversion for wildlife, you can regulate groundwater pumping, you can protect wetlands, you can support best management practices among stakeholders and communities, and this has been very effective regionally in many areas of the country, and we often take it for granted. And lastly, we have to start enforcing atmospheric emission standards. And these are just some of the many things that we need to do on landscape scales, or our protected areas are not going to be successfully maintaining themselves in perpetuity. Okay, I want to move on to a case study of a national forest where I've been working for the last 15 years in Puerto Rico. Puerto Rico is a commonwealth of the U.S., and it has the largest intact contiguous piece of old-growth forest in the Caribbean. It's called the Caribbean National Forest, and it's about 100 kilometers squared. It's in northeastern Puerto Rico. It's only 25-minute drive from San Juan, and it's got 9 different watersheds as depicted here. San Juan is located right up here. Puerto Rico's got one of the highest population densities per land unit area in the world. Very crowded. Now, when I started working there looking at the effects of shrimps in stream ecosystems, freshwater shrimps, I had no idea that so much water was being extracted from the forest. And in the early 1990s, a master's student did a water budget, actually accounting for where all the water was going. And she showed us in her budget the location of water intakes where people are withdrawing water from the forest or from rivers draining the forest just outside of the forest boundaries. So all those little white spigots you see are water intakes. All the little orange dots you see are sewage treatment plants. There is so much water withdrawn from the forest that there's not enough water to dilute the sewage coming in from those sewage treatment plants. Imagine all of the tourism and development on the coast here to support tourism, golf courses, hotels, and it's really a problem. This is what one of these water intakes looks like. It's a low-head dam. It's only like 5 feet tall. And then there's a water intake. Boy, I sure can't multitask here. A water intake right here, where water is being sucked into municipal water supplies for potable water supplies. What this water budget told us is that on an average day, 50% of the water draining from these 9 rivers gets sucked in to municipal water supplies. It does not get to the ocean. You've got a lot of saline water intrusion up to the dams. In fact, all 9 rivers in the Caribbean National Forest have these low-head dams and these water intakes, except for one, the last free-flowing river, the Rio Mamaeus. Okay, so what does this mean to the ecosystem? You don't have salmonids in this system, though Puerto Rico tourist shops sell pictures of beautiful Puerto Rico t-shirts with salmonids jumping up over a dam. But what you have here are migratory shrimps and fishes, a very simple food chain dominated by shrimps. And the shrimps are listed here. Their names aren't important, and I won't go into that, but I just wanted you to know that in these headwater streams, you can look into this stream and see 25 shrimp. They're being entrained and sucked into the water supplies, and they're dying. Here are the animals, the different species of shrimps. The largest one here, Macrobrachium, it's edible, gets to be about this big. People like to go in and harvest them recreationally and eat them. I put this in here to remind myself to tell you that the shrimps can migrate upstream as juveniles, and they do this in long chains or parades. And they can actually walk up waterfalls. As long as there is a wet rock face and they perceive unidirectional flow of water, they can move up that rock face. The fishes cannot. The fishes prey on the shrimps. So once the shrimps get above the waterfall, they're living this predator-free existence, just competing with each other. And these animals have a big effect in the ecosystem. They scrape the rocks with their fans. This is a Atia shrimp right here, and it's got its fans out. It's using them for filtering here, but it actually will use them to scrape also. This is important because they're eating all the algae in the system, and we find that when they're extirpated and completely lost from an ecosystem, you get algal blooms and you get a lot of sediments coming in, and the water looks dirty. Here are some of the fishes in the system. Here's the predatory fish that feeds on the shrimps, a little algal feeding goby, and an eel. But that aside, how do these water intakes kill the animals? Here you have a water intake above this Lowhead Dam, a non-functional shrimp or fish ladder. When there's no water going over the dam and it's all being sucked into municipal water supplies, all the animals get entrained into that intake there and they die. And we basically got money from the USDA Forest Service, my graduate students and I, to quantify this. Here's just a snapshot of our data here. You've got larval shrimp mortality on this axis here, the percent of larvae entrained. Discharge is the blue. The white line is the mortality of the shrimp. When you have no discharge over the dam, you've got 100% mortality of shrimp. When you have 100% discharge over the dam, you've got low mortality of shrimp. They looked at all the U.S. Geological Survey gauging stations and modeled shrimp mortality and found that it was extremely high, and that, in fact, the recruitment of adults upstream could be affected and the whole ecosystem could change because these animals are very important in determining ecosystem processes. And my student published this in Ecological Applications in 1999. Because we're working with the USDA Forest Service, this data was immediately put to use. And that's what's been wonderful about our collaborations with them. They took this data, went to the Aqueduct and Sewage Authority, and said, listen, if you devised better water intake systems, perhaps you could minimize the mortality of shrimps. And to our amazement, the Forest Service, the Aqueduct and Sewage Authority did just that. They actually, good, okay. I don't know, the other system shouldn't be on. In any case, they decided to, instead of building a dam on the last undammed stream draining the Caribbean National Forest, they put in a French drain system where they sucked the water out of the center of the channel. And so this data, I believe, was very instrumental in not getting this last undammed stream dammed. And they put in this new water intake. Some of the other recommendations that the grad students made in this paper is install functional fish ladders, maintain minimum flows, fix leaky pipes. In contrast to the irrigation canals in the Bitterroot Valley that I've been hearing so much about lately, that are leaky and actually recharge the groundwater and increase potable water supplies for residents of the Bitterroot Valley, the leaky pipes in this instance are losing the water completely to the system because of the karst topography. It goes down into a saline aquifer. And so we think that by fixing these leaky pipes, it would really go a long way towards preserving water for both humans and nature. Okay, I just want to mention a few of the environmental outreach things we've done to try and promote public awareness in Puerto Rico of hydrologic connectivity issues. We developed these posters. And this is from an inset on one of the posters, and it's a geographic information system generated diagram of the Caribbean National Forest showing the location of all the water intakes that are disrupting the connectivity of the system. And the poster is called Balancing Human Water Needs with Biological Needs. And in the insets, it's got a picture of the French drain system that's effective by not killing the shrimps, and another picture of the more damaging dam and water intake. Here's another poster we created with an artist did it, showing the river continuum from the headwaters to the estuary, with the shrimp-dominated assemblages in the headwaters. Here's one of these dams, water intakes, and here's the estuarine flora, fauna, including a manatee, which is now extirpated. You don't find these there anymore. But we wanted to have the original fauna represented here. The school children are getting these. They're disseminated across the island so people can better understand the resource value of these stream ecosystems. The USDA Forest Service also funded this. And in all I'm learning about the water quantity issues and quality issues in the Bitterroot Valley, it strikes me that you could make some pretty effective posters showing the groundwater, surface water interactions there for similar outreach purposes. So we're really concerned now in the Caribbean National Forest. What are the cumulative impacts of water withdrawals on the biological integrity of these streams? Also, how are droughts and island-wide water shortages exacerbated by this burgeoning human population going to affect water withdrawals and the biological integrity of the forest? You can see what kind of thing we're up against here. Here's the city of San Juan, Puerto Rico in the foreground. There's the Caribbean National Forest in the background, 25-minute drive. Urbanizing communities, rural urban sprawl between the city and the Caribbean National Forest. So this is no easy problem to solve. Okay, moving on to one of the last parts of my outline here before I get to future challenges. I want to talk a little bit now about the interacting effects of altered connectivity and contaminant transport. I just wrote a book chapter about this because I realized that I couldn't find in any one place something that summarized some of these regional and global trends that were occurring of how hydrologic alterations were interacting with contaminant transport. And I came up with these 4 trends. I don't have time to talk about them all, but I want to talk about 2 of them in a little more depth. The first, effects of wetlands loss and contaminated irrigation drainage on wildlife. And I also want to talk about D here, dam removal and the upstream transport, ooh, I did it again, of persistent contaminants. I thought by not using PowerPoint I would avoid all this. Okay. I'm sorry. It's okay. Okay. I think I'll just leave that alone. I won't even touch that anymore. The area of irrigated land in the world is expanding. And the thing that's of concern to me and should be to all of us is that wetlands drainage in combination with contaminated irrigation drainage within the remaining wetlands is causing wildlife to be dependent on contaminated water supplies. We drain wetlands to make agricultural areas like this, and then we irrigate them with the remaining wetlands available, or groundwater. That water oftentimes becomes contaminated with natural salts in the soil like boron and selenium. It's particularly in arid areas of the West. And then it contaminates the remaining water supplies that wildlife are dependent on. This is not just happening in the arid areas of the United States, it's happening in the Macquarie swamps in Australia, it's happening in the Aral Sea in the former Soviet Union. So the resultant impacts on fish and wildlife are really severe, given that the remaining wetlands often constitute a small portion of historic wetlands. The Salton Sea is now the largest water body in California. It was artificially created when they were trying to divert the Colorado River, and it broke through a dike and went into an old seabed. They now created the Sonny Bono Wildlife Refuge there. The area is so contaminated by toxic irrigation drainage that one of the main activities of the Fish and Wildlife Service personnel is to run an incinerator to dispose of the dead bodies of birds, which are dying of avian botulism because they're all crammed into this polluted area, in essence. And this is probably not news to you because you live in the Pacific Northwest and you're hearing about this. The Sonny Bono Wildlife Refuge is not the only one that's having problems like this, though perhaps the most dramatic. I wanted to show you this map that shows you areas that are very susceptible to contaminated irrigation drainages, those areas in the shaded brown. Here's the Salton Sea Sonny Bono Wildlife Refuge. Here's the Kesterson Refuge. It was once a wildlife refuge when it was actually just an artificial wetland created to contain contaminated irrigation drainage. So much wildlife was attracted to Kesterson that they called it a wildlife refuge. And then the animals started to die because of selenium accumulation. So they called it a toxic landfill, and they withdrew it from the wildlife refuge system. The Sonny Bono Wildlife Refuge is still active. There's other ones throughout here that are receiving contaminated irrigation drainage from federal projects. The Salton Sea, well, I can't remember the exact names, but number 2, 7, and 4, and 8 are all wildlife refuges. On the bright side, the USGS is making maps trying to show what areas, based on geography, geology, and climate, are most susceptible to contamination from salt buildup from irrigation drainage. And they've mapped this, so it gives us a predictive tool to at least know where certain farming practices, certain irrigation strategies really aren't sustainable in the long term. So on that note of hope, I'll end this little case study and just say that as a society we really do need to proactively reevaluate unsustainable agricultural practices. The last trend I want to mention here is how dam removal can interact with exotic fishes to cause contaminants to travel upstream. So how does that work, you might ask? Well, the situation is very complex. Dams oftentimes serve as barriers, isolating upstream food webs that can be bad. But in this sense, when you have contaminated fishes downstream, like in the Great Lakes area, where lots of pesticides and PCBs were dumped into the Great Lakes after World War II, when you remove dams, you run the risk of having those exotic game fishes that were stocked in the Great Lakes move upstream with their pesticide loads. So dam removal may foster the introduction of bioaccumulated toxics into relatively untainted food webs. Here's the Great Lakes watershed. Right now, or just recently in the last year, 3 dams were up for removal because they were pretty obsolete and serving no function. However, it was decided not to remove them because they were keeping contaminated fish downstream and not allowing them to get into the habitat of bald eagles that were not previously feeding on contaminated fishes. And this data shows it really well. It's not my data. It was published in the new ESA's Journal of Conservation Applications. And you can see here that this is the wildlife protection value of PCBs down at 0.16 parts per million. And in Lake Michigan, it was way up at 2. Ontario, Huron, Erie, Superior, it's over the limit. And this is the concentration in fish in a fish-based bald eagle diet above and below the dams for 3 rivers in Michigan. These dams they wanted to remove. This is above the dam, this is below the dam, above, below. So that data speaks for itself. So this is a real issue, and it's going to occur throughout the world as people start to wonder if they should remove dams or not. It's certainly not an issue when it comes to the situation or the possibility of dam removal here in the Bitterroot wilderness area because there are no contaminants like this. Okay, I want to end up with just some questions to leave you with, particularly the students that are taking this class. We really don't know how hydrologic connectivity operates in different landscapes. We've got to improve our hydrologic understanding. How does hydrologic connectivity differ link different ecosystem types? How does it link the mountainous ecosystems of the Selway Bitterroot Wilderness area with the valley? How are the time lags between a given alteration in hydrologic connectivity and consequent ecological effects on biodiversity? What are those time lags? How do alterations in hydrologic connectivity affect food webs? How do cascading ecosystem level effects of food web alterations affect both aquatic and terrestrial ecosystems? Let's follow the cascade up the food web to look at the terrestrial effects. How do the interactions between human and natural disturbances affect hydrologic connectivity? In the Selway Bitterroot National Refuge, wilderness area, as you get increasing droughts and potential global warming that's going to decrease the amount of water running out of those streams and decrease the amount of water available for irrigation, sheet flow irrigation, how will the water table be maintained in the valley to support increasing human populations? As more and more agricultural land is retired and you have decreasing irrigation, will the groundwater levels drop such that the increasing urbanizing communities will not have sufficient water? What will the time lag be? These are all questions that we don't know the answers to. And lastly, I just want to bring home the point that we really do need to incorporate a better understanding of hydrologic connectivity into the field of conservation biology. We have to be considering watersheds and regional aquifers and wind and precipitation patterns. If somebody asks you why polar bears had the highest PCB concentrations ever measured in mammals, would you know why? Can anybody raise their hand and say they know why?
Atmospheric shift of pollutants.
That's right. You've got a lot of PCBs that are in the atmosphere. They volatilize in warmer atmospheres and condense in the colder north latitudes and get deposited in the polar areas. And ocean currents also take them that way. And they get taken up in the food chain by the fish, and who gets the brunt of it? The polar bears and the Inuit Indians who eat the polar bears. When scientists went out to try and find a reference population of humans to get low levels of PCBs, they went to the Inuit Indians and were just blown away to discover that they had the highest concentrations they'd ever found. Now that just shows you what a poor predictive understanding we have of hydrologic connectivity. And all these facts are out there, but no one's synthesizing the information to make good predictions. Here are some more questions. We really need to consider the ecological and socioeconomic trade-offs associating with altering hydrologic connectivity. How can we balance long-term ecologic and public health benefits with short-term economic gains? And so on. So I want to end with this quote that Sandra Pastel made in her book, The Last Oasis. In the end, we may need to develop a new water ethic, in a sense an ethic that says it's important now to begin sharing water with each other as well as with nature. And I just want to acknowledge all the people that have made my work possible, and a lot of the federal agencies and representatives of those agencies that gave me a lot of the information to sort of do this sort of global synthesis of hydrologic connectivity. People from the National Park Service, the Fish and Wildlife Service, the USDA Bureau of Land Management, and so on, and also my grad students and colleagues. Thank you.
We have time for a few questions.
On the title slide behind the word, what does that show?
The title slide. It's a small piece of land, forested land, in the middle of an agricultural field that was just left there.
Looks like there's water around it.
It was agricultural land around it.
Got it, good. Thank
I just put it in there because it was an interesting
you. Got it.
landscape view. Yes.
You spoke a little bit about the position of protected areas in the landscape, but you showed several different parks, and you did not mention any of the arbitrary boundaries that are used to delineate the parks. And I wonder, when you're talking about hydrological connectivity, how can you leave that out?
Oh, that's a really good point. Somebody mentioned this morning when I gave this talk that one of our old presidents, Crowley, was saying that political boundaries should really follow watershed boundaries, when in fact they don't.
That was John Wesley Powell.
That's right. Okay. It's a shame that the parks, and we haven't given more thought to where parks and reserves are located with respect to watershed boundaries and regional aquifers. I haven't talked about that. It's just a quagmire. Kruger Park is located on the border of Mozambique. Mozambique's upset because not enough water is getting into Mozambique. The park's upset there's not enough water to maintain the animals. There's so many transboundary issues here. And it's interesting that the Selway Bitterroot wilderness area actually has a boundary that falls right at the Continental Divide. Is right there between Idaho and Montana.
I thought it was the continent.
No, it's Bitterroot Divide.
It's the Bitterroot Divide.
So anyway,
I'm sorry, I didn't address your question. I've avoided the issue completely. I don't get.
I just thought it was kind of curious because of some of the other things that you mentioned, such as enforcing emission standards. We certainly are in a position to do that when we don't sign international protocols and such. So, the one thing that we can change is at least the boundary of the parks. Anyway, that's just something I noticed.
I think we can change emission standards here in the U.S. I think we really have to. I didn't get a chance to talk about methyl mercury in reservoirs because of all the incineration and practices that release inorganic mercury into the atmosphere. This mercury is building up in the ecosystem and then getting changed into methyl mercury within the anaerobic sediments of reservoirs. It's another example of a hydrologic alteration interacting with a contaminant, creating conditions for it to get mobilized and into the food chain. We have to control atmospheric emissions because the fishes in all of our stratified reservoirs are building up mercury contamination levels that are affecting humans. And there are mercury advisors in like 40 states, excuse me. And I think we have good hope because of the human impact there of reducing mercury emissions. And I think I agree with your cynicism about how we won't even sign international agreements, but I have to stay hopeful. Yeah.
The last slide you showed, you had a whole bunch of different federal agencies that you went through, but given the agency's historic lack of cooperation between one another and the fact that hydrological systems span local, state, and federal areas, who ultimately is going to have jurisdiction to make any changes?
Go ahead. Maybe I should defer to my colleagues at the Leopold Institute. I mean, I see it, and I think I should actually, but personally I see it as small steps. I mean, places like the Leopold Institute interact with various agencies and try and bring people together to the table, stakeholders in different agencies, and that's really all we can do is try and work together. How's that for avoiding the issue?
Maybe not much as a question of jurisdiction, but responsibility. Right? Whereas it's more of a personal thing between people within agencies than it is, a jurisdiction.
You can see I'm between a rock and a hard place here. Here I am, a pointy-headed academic. I can't speak for my federal colleagues. In fact, when I first wrote the paper synthesizing all this information, I was very worried that there would be resentment that an academic was taking this role, because I certainly don't want to appear critical. Yes?
I've got two questions for you, connected, of course. The first one is, how successful has your Florida Region project been? Has it been very successful in returning water into the streams, getting the dam modifications made? And second thing, what happens when you get past that education stage? Because I know that I came from Washington with the salmon controversy on Columbia and Snake Rivers, where a lot of people have a lot of different opinions, but there's been a lot of research done and publicized on the connectivity of the Columbia and Snake River ecosystems, but they still hold these opinions about we don't need water in the streams, we need to barge the salmon, things like that. How do you go about changing those opinions and working with that when they understand the connectivity?
That's a really good question, and I'd love to be able to say, oh, we've thought about all that. But again, we're just thrilled as scientists that have been keeping our heads in the sand pretty much, working up in this pristine forest, that we're finally making some management connections and doing some environmental outreach. And as an academic, I must say, you don't see that very often. And I'm not patting ourselves on the back here, although it may sound like that. It's because we're working with the USDA Forest Service. They have certain management needs, and they say, hey, listen, pointy-headed academic, I'll give you some funding, but you can do this, not just go count the number of chelae on a shrimp's head. I feel like it's been pretty successful, the outreach activities. The kids all take these posters home. We've developed programs in Costa Rica for outreach. But we're not in the field of education. We don't follow up as to the success of our outreach activities. After all, I'm an ecologist sort of branching out doing this because I was hired as a conservation biologist. I don't know if that answers your question. Yeah.
You mentioned the Bitterroot Valley. I'm a resident of the Bitterroot Valley, and I've watched development along the floodplain, which you mentioned. Floodplain development is, to me, a major threat to our rivers, particularly, in sensitive rivers like the Bitterroot that have a broad meandering floodplain. In addition to floodplain development, we're seeing stabilization projects where people are not only building, then they want their properties to be stabilized, so they don't want to lose any property, the natural process of irrigation. I'm hoping that some people in this room, in the next 25 years or so, get a handle on development. It's really hurting our river systems.
I'm just learning about the situation that the valley faces right now, and I guess we're going to Hamilton tomorrow to talk to the Forest Service personnel about specific issues there.
Chris Clancy.
Any other questions?
So let's thank Catherine for coming and talking to us.
Right here.